He will present about the emergent chaos in the Turing-Smale problem.
Thank you very much. It's a pleasure to be here. So I'm Tiago Pereira. I'm a professor of mathematics in the Institute for Mathematical Sciences and Computing at the University of Sao Paulo. I'm a honorary professor of mathematics at the Imperial College. And recently I have this partnership with the Weierstrass Institute through the Humboldt Foundation. I think it's my fourth time here, or third. Every single time I have a great time. So thank you very much for the organizers to put this together and for the invitation. So this is I'll present some joint work that I did with 3 colleagues. So this is Dima Turaev. He's a professor of mathematics at Imperial. He's like being one of the most influential people in my career. So he was a student of Shunikov, and the word Shunikov will appear here quite a few times. This is Fernando Queiroz. So he's one of the authors of this paper. He was my PhD student. So this was part of his PhD. So his PhD ended up being awarded the best PhD thesis in mathematics in Brazil in 2023. And this is Eddie Neiholt. He was a postdoc with me at University of Sao Paulo. He's now has a position at Imperial. But he liked Brazil so much, he wants to come back. So maybe in the future he's here. So Fernando is looking for jobs now. So he's been very well trained. So this work appeared in Communication Mathematical Physics. I will not give you the details, but the paper is there. You also feel free to send me any comments. And by the way, I like very much when people interrupt me during the talk. So just feel free to interrupt at any time. Okay, so the big inspiration for this work is I mean, historically, I'm not an expert in the history of this problem, but apparently Turing in the 50s, he starts saying how cells will multiply and will evolve. So he called this the problem of morphogenesis, and apparently this means like how cells they get specialized and how they form patterns. I think this is like from single cells how you can get to patterns. And so he had the following interpretation. So you have a bunch of inert cells. So cells by itself, they do not do anything. They'll just sit there. And they say, okay, how do these cells interact? And Turing's idea was they interact via diffusion. There's some ionic diffusion in the medium. Okay, so this ionic diffusion will lead to pattern formation. I think now this is a well-accepted thing, but in the 50s, people thought this is just very stupid because diffusion should just equalize things, never lead to pattern formation. But I think Turing was slightly ahead of his time, so this was his interpretation. Yeah. So this means like cells by itself, they do nothing. They just sit quiet there. Now they start interacting. This interaction is diffusive. And because of diffusive interaction, you have pattern formation. So you have oscillations in the system and so on. Okay, I'll put the equation now so that we're in the same page. So let's discuss, this will be the particular version of what I call the Turing problem. Okay, so alpha here, just set it to 0. Alpha is the coupling strength. Set it to 0, forget everything that appears in the summation. So what do I have here? I have x dot, this will be modeled by my cell. X dot equals to f of x. So this will be, and I'm assuming that now x dot equals to f of x. This has a globally stable fixed point. So what does this mean? It means like the system by itself will do nothing. So if I let it run, we'll go to the fixed point. Nothing interesting happened. And I'm saying that this is globally stable, so it doesn't matter where I start, I go to the fixed point. So this is trying to capture this idea that Turing had that cells are inert. So nothing is actually going on if you do not have coupling. Okay, so now the system is super boring if I don't have coupling. I'll turn on coupling. So now alpha is positive. So in this case, J will interact to I according to this matrix that we call adjacency matrix, so Wij. So this means like J will be neighbors with I. So we've seen this graph yesterday quite a few times. If this Wij is 1. So we saw this in Guilherme's. His case was more complicated, right? So it was 3 things. So here's simple, only 2. And what I call diffusive here will be the following. So this D is a positive definite matrix. Yeah? And diffusion for me now means the following. So the strength of interaction only depends on the difference of states. Yeah? This is what I call diffusion. So kind of osmosis, yeah? Or Fick's law you can think about. Is the model clear? Yeah? So if the model clear, I'll go on. So basically I have a few things here. So I have F models the isolated problem. D, I will call the coupling matrix. Is diffusive. Diffusive means it's positive definite. And whatever it means diffusive, depending on the different states, and I have the graph, Wij. Yeah? So this will be the goal of this thing. So let's see here the problem that we have here. So if alpha is 0, then the coupling vanishes. And by assumption, every trajectory will go to the fixed point here. Dynamics is super boring. If alpha is small, then there's this theorem that's actually easy to prove. It says that if things are going exponentially fast to 0, under small perturbation, they still go exponentially fast to 0, so nothing changes. So this means for small coupling, nothing changes. If alpha is very, very big, then what happens? So then F becomes a perturbation of the diffusion, and diffusion equalizes everything. So this means I have one case where everything's going to 0, and one case where diffusion is dominated, so everything's equalizing. So kind of this pattern formation doesn't have much room. So that's why people thought that in the 60s you had lots of these papers and the diffusion never lead to pattern formation. So this is why this problem was interesting in the beginning, because people saw that for weak interaction, nothing happens. For big interaction, you equalize. So this means whenever something's interesting in this model, then you must have intermediate interactions. And in dynamical systems, you only use to perturb things, right? So either things are very small or very big. So if you say something is kind of not too big, not too small, usually people are very lost. Yeah, so this is just to say that any interesting behavior that you can see in the system must come for intermediate coupling strengths. Yeah? Okay, but then in the 70s, Ismail entered this problem. He took this model, and he only considered 2 coupled systems. So here I have N. He considered 2. And he showed that this problem, the Turing problem, can have oscillations. Yeah. And then he proposed, actually he discovered a mechanism, he gave a mechanism for oscillation. This is called Hopf bifurcation. So let's discuss this Hopf bifurcation. So here. I'm discussing this because this will appear again, so why not to discuss now? Imagine that I have x dot equals to f of x, and I linearize the system around 0. So this is the Taylor reminder, and this is the linearization. So here now I will plot, here's the complex plane, and I'm plotting the spectrum of A. The spectrum of A can be very complicated, so these are the eigenvalues of A. So let's say, if the system is isolated, then I have spectrum only in the left part, because I'm assuming that things are going exponentially fast to 0. But what I will do now, actually what Ismail did it was to say that I have a parameter here, then I have a parameter here, therefore I have a family, And what Smale discovers that a pair of eigenvalues can come because of this coupling and cross. At the moment of crossing, he proved that there is a periodic orbit of the system. And this periodic orbit, actually this pair, the pair crossing of the eigenvalues is related to the coupling. So this is what he proved. I'm just saying because this will be very important object. So you have a spectrum of the linearized operator, depend on parameters. So you change parameters, you have curves. And whenever they hit the imaginary axis, something interesting happens. This is called bifurcation theory. And then Smale said, okay, so I gave one example in 4 dimensions, 2 systems, problem. Classify all possible vector fields F and all possible coupling matrix D, such that the Turing problem has a Hopf bifurcation. So this is a chapter in the famous book. The book is called Hopf bifurcation. You have this book, right? No, I think I saw in your... So Hopf bifurcation, this book. So a very famous book by Marsden. Yeah. Okay, so then people start working on this problem. So they start slowly marching and so on. So in, I think, 98, there was a major contribution. This paper is called, by these 3 colleagues, is called diffusion-driven oscillations. So basically, they proved that for regular networks, you can have oscillation-driven. So this means, like, if your network is like this, I mean, the ring that we saw yesterday in the talk. So here I have my cells. If they are interacting in this ring, then they prove that you can have Hopf bifurcation. So after they proved this this theorem, I think then in 2004 they had their final paper. So they give conditions for any network to have Hopf bifurcation. So basically they solved the Turing-Smale problem for periodic oscillations. But then these colleagues, they coupled 2 chaotic oscillators. So when they couple these oscillators, they are inert. They put a resistor in the middle. Resistor is also a diffusive coupling. And they saw that once they are coupled, I mean, they did it numerically. They actually don't know. But if you compute the favorite things like Lyapunov exponent, divergence of nearby trajectories, so box dimension, everything indicates that the coupled system now has a chaotic behavior. So this means like, okay, there's also a problem. So Smale proposed to solve for periodic oscillations. So after 40 years, people did solve. But now they saw that something else can happen, which is chaotic oscillation in the problem. And the question now is whether you can prove that the system has chaos. This problem then became open for, I think, 10 years. And then 3 Spanish friends, they took 2 systems. Now it's very specific to this system. The system is called Brusselator. It's oscillators in 3 dimensions. They do a very specific coupling, very specific parametrization. And they prove in these 2 systems, coupled, you can have chaos. So now we have the following problem. So the Turing problem was solved in generality for Hopf bifurcation. And we have one example of one particular system that when you do this Turing coupling, it can have chaos. So then, Fernando came to me and said, okay, let's do the PhD together. And I said, okay, I propose you to solve the following problem. Classify all triples now. There will be F, the local dynamics, D, coupling function, and W network, such that the Turing-Smale problem will accept chaotic oscillations. So the first time he said, no, this is too hard, he dropped. And then he went to study topology. And then after 1 year, he said, topology is too hard. Let me go back to this problem. Okay. But I was working on this problem already for a couple of years with Dima Turaev. Anyway. So let me skip and give you the This will be two main results, and I will obtain chaos as a corollary of these two main constructions. Yeah? The first result, this is informal statement. The formal statement is like, makes no sense to state. It says the following. So when the isolated system, so this F, satisfies certain conditions, whatever this means, there is a positive definite matrix, D, and a positive coupling strength alpha, such that the network as a whole has a reduction to a low dimension. Let's discuss this statement. Let's make sure that we are all on the same page. And I'll explain what I mean by certain conditions. Because maybe you're wondering, man, if I just write certain conditions in a theorem, I can just prove any theorem, no? Okay, so let's say, what's the dimension of my system? So the idea is the following. Each isolated has dimension n. And then I have a bunch of oscillators. So I have capital N oscillator systems. So this means the dimension is very big. Dimension of the system will be N times big N. So usually this is the problem. So when you try to understand this problem, this big dimension can be anything because N can be very, very large. So usually we get lost here. But this is saying that if the isolated system satisfies certain condition, that I will tell you which condition it is, then instead of looking at this huge dimension, I can look at, say, 3 dimension or 2 dimensions, and this will describe the full system. This technique that allows you to do reduction is called center manifold. So let's discuss this idea. I will have here some system that will have very low dimension. I will do a particular case where I have dimension 3. This will be the main construction I'm going to do, but I can do any dimension. And here I put 3 dimensions. In this axis, I have a huge dimensional system. So everything that's left is in this axis now. Does this make sense? What I'm going to prove now is that this whole system, I'm going to have a set. This is called WC. This set is a graph of a function. And is invariant. So this means if I give initial conditions to my system on this graph, I stay on this graph forever and never leave the graph. And if I take a point that does not belong to the graph, let me call y, and I'll call this x. So then there is a function. I will call this h, such that y becomes a function of x. So this means I have this graph. This guy is invariant. So this means if I never leave the neighborhood of the origin, I always stay in this graph. The flow cannot take the things away. And whatever is not in this graph, so if I take a point outside of this graph, this is actually total, the dynamics of this point is totally given by what's happening on the graph. Yeah? So this is very strong. So in science, people had this idea to do reductions, right? So this is the main theorem. So you can always do this reduction. And this is super precise, you lose nothing. Yeah? Yeah. So this is called the center manifold theorem. So what I'm going to do now is to construct the center manifold for this Turing-Smale problem. If this construction is not clear, then we can discuss more. But there are multiple ways to define this WC. You can think of just define as a set. It's the set of all points that cannot escape exponentially fast or cannot go to the origin exponentially fast. You can prove that this set is a graph of a function and this is the function. Okay, so, but to construct the set, I need some assumptions. What's the assumptions will be the certain conditions. And the condition is the following. So, this is the Jacobian of my isolated system at 0. I'm calling A. And let's return to this picture. I just said that A, the system is stable. And if you recall your differential equation lecture, if you say your system is stable, this means like the spectrum of A must have real parts negative. There's no other way. If the system is stable, all the eigenvalues of A must be in the left part of the complex plane. Okay, so all the eigenvalues of A is in the complex part, is in the left part of the complex plane. There's no other way, just because I said the system was stable. So this A has negative eigenvalues, the real part. But now I have this condition, and this will be the main condition to prove the chaos in the problem. It's saying that there will be m vectors such that the sandwich is positive now. Okay, so what is this saying? This is saying that A is very far from Hermitian. A is very far from being symmetric. Because you recall, right? So this is related to the talk of Guilherme yesterday. If A was symmetric, then this had to be negative. There's no other way. But now I'm saying I have a matrix with a negative spectrum, real part, but when I sandwich between this quadratic form, it gives me positive. This means like I'm very skewed. I'll give you 2 examples. This matrix B is a symmetric matrix, right? So because B equals to B transpose. So the theorem will never apply to this matrix. If you sandwich any vectors between B, V, B, V, this will be always negative. There's no other way. This matrix now, I tell you, A is Hurwitz. Hurwitz means like the spectrums in the left part of the complex plane. And satisfy the skewness condition. And okay, now I have to construct which vector is it and so on, but you have to trust me now. Yeah, so basically it's the following. So you see, this 3 here, so I'm telling you the following. The spectrum of A is negative. But what's happening here? So you see this -3 is much bigger than this one. So it's a skew in the matrix towards asymmetry. And this is the main condition. So basically it's the following. Everything that I'm telling, so you can look at your problem, you linearize, look at your matrix. If the matrix is very symmetric, man, you never see anything in this problem. If the matrix is very skewed, then you're going to see lots of interest in dynamics. So this will be my main claim. Yeah? Okay, so you see, I have, if there are m vectors, then I can prove to you there will be reduction to dimension m. So in the case that I'm going to prove soon, I'm going to assume that I have m equals 3, so I have reduction to 3 dimensions. In the case of Turing problem, because of Hopf bifurcation, I had m equals 2. So if this is satisfied for 2 vectors, then I can prove, as a consequence of my theorem, the theorem of that other people proved. So if this is clear, I'll tell you how to get to this point. So this is just, so I start with the system. The dimension is very, very, very big. So what I want to do, I want to get rid of all dimensions that are not important for me. And I choose to do in the center manifold way. So let's say step 1. So if I want to prove this theorem, step 1 I will call linearization. That I have now x. X will be my big vector of vectors. So this vector now is sitting in this huge dimension space. And I linearize the system. So this will be a big linear operator plus nonlinear terms. And what I'm going to do, so this, everybody that studied this kind of, I think you also do this, right? So you want to study the system, so you do your linearize and nonlinear terms. And what I do, I block diagonalize this. So when I block diagonalize this operator will split into blocks of the following form. So A minus, I don't know, some number here, D, and then another block here, A minus some other number here that I don't know, D, and so on. So this will be the structure of the linear part of the operator. So you see that it's important now to study the blocks of the form A minus D. So where A is the linearization of the isolated system and D is the coupling function. Yeah, if A is antisymmetric, the system cannot be stable, right? So then it cannot be Hurwitz. Yeah. So that's why I have this small proposition here. It's saying the following. So now so this is a general proposition. So just let's read like this. So you take any matrix, n by n, and assume there will be m mutually orthogonal vectors, v1 to vm, such that you have the skewness condition satisfied. Yeah? So this skewness condition is satisfied now if and only if there is a positive definite matrix D such that A minus D has M0 eigenvalues, so but has algebraic multiplicity M. So this is saying I have to study this, and this proposition is saying if I do A minus D, in some coordinates, this must be a Jordan block of dimension M, and here's something that I don't care. So basically it's the following. So all this works to do the following, is to remind you that you studied this Jordan block in your linear algebra class. No, they don't need, no. They don't need to be eigenvectors of A. No. If they were eigenvectors of A, this would have to be negative. Yeah. It's just, let's say, the action, A is very skewed, and A will skew some vectors to positive. So basically, it's only saying the following. So if you take your isolated system, so let's do an interpretation like this. So let's forget about everything that I said, and you have just an isolated system. You give an initial condition. This is going to go exponentially fast to 0 by assumption. But so you can read this skewness condition like this. So before it goes exponentially fast to 0, it will grow for a while. Yeah? So you've seen this before, right? So you give an initial condition, first it grows, and then eventually goes to 0. So this is what this means. Yeah? So, and then this means, like, if it's growing for a while before it goes to 0, there will be a chance to cause instability in the system. But this here's just to do the following. So I have A is given, and this theorem is a theorem about the existence of a coupling matrix D. So this G is depending on A, such that when I do this trick and I look at this difference, then I have a Jordan block. This is basically what this means. So let's study this. So here's the spectrum of A, and I'm doing this case for M equals 3, which will be the interesting case. So here's the spectrum of A, so -1, -2, and a complex eigenvalue. And then this will be the spectrum of A minus D. This means like -2 now went to -4, why not? But these 3 eigenvalues here went to 0. So I have a Jordan block now. Yeah? So this will be the whole construction of this thing. So this means I go, linearize, blah, 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 block diagonalize, do whatever I want. Now I cook a Jordan block, and now I enter a area of mathematics that is just saying I will unfold the Jordan block, and what I want to prove is that if I unfold the Jordan block for dimension 3, I can get any dynamics I want. Okay. So this is just, so let's recall, there will be a painful technical part. So here's my WC. Here's my dynamics. And I want to, I have a vector field here. And what I want is a vector field in WC, right? I want a differential equation in WC. So there is a procedure saying that if I have a vector field in the whole system and this is enslaved by what happens here, then I can just write a vector field on WC. If you do the calculations, they're painful, but you can do it. But when you do it, for this problem, you realize that the problem becomes these nonlinear terms. Because it can happen like you spend this in a Taylor series, and then you write the Taylor coefficients of the system in WC, and they ended up dying. Nothing forbids this. So let's say all quadratic coefficients will die. And then for a number of years, we thought this is an impossible problem to solve, and then Eddie came up with a very nice idea. So he realized he constructs a condition on the graph such that these nonlinear terms will never die. Yeah? So that's why we say now, for certain networks, and I'll explain to you which certain networks this, after the reduction to low dimensions, so this means after it writes the system in WC, all the nonlinear parts are generic. So this means if they were non-zero before, they're non-zero now. And this is super important in this field because you did the nonlinear parts to survive, so you can do bifurcation theory. So basically, you want unstable manifolds to fold, and you need the nonlinear terms. I told you there's this word here for certain networks, and now I'll explain to you what certain networks mean. Okay. The certain networks will be explained in terms of what people call the Laplacian matrix of the graph. And I think Guilherme explained this yesterday, no? You did. It appeared. So let's recap. So the Laplacian matrix of the graph will be called, will be this matrix, K minus W, where W is the adjacency matrix, and K is the matrix of degrees. So on the diagonal of this matrix, I put the number of connections you have. And there's some standard thing here. So for example, if the graph is undirected, so G has only real eigenvalues. 0, the multiplicity of 0 as an eigenvalue, counts the number of connected components, right? And the spectrum can be ordered in this way. Okay, so this is just, I'll need this in a second. And if what the Laplacian matrix is clear, I'll move on. Otherwise, I can give a few examples. And now this is the main definition in this part. And this will classify all graphs where the Turing-Smale problem has a solution. I will call the graph rho versatile if is the following. So there is an eigenvalue pair. So mu is an eigenvalue. Nu is an eigenvector. They are simple. Mu is a simple eigenvalue of the Laplacian, such that when you look at the eigenvector and you try to solve this equation will be non-zero for L starting from 2 to rho plus 1. Does appear a technical condition in the proof, but apparently now I discovered there's a huge combinatorics behind this, and I'll try to elucidate this a bit. So first of all, this is trivial for every L positive, right? For every L positive, of course, this is positive, because you take a number, positive or negative, you raise to a power 2, will become positive, your sum is positive. So this means I only have trouble here for L odd. And the problem is if this guy vanishes. If this guy vanishes, the reduction will not work. Yeah? Let me give you some examples. So I have this graph, 1, 2, 3. So this is the Laplacian of the graph. So let's see whether the diagonal is correct. No, let's not check everything else. But in the diagonal, it sits the number of connections of the nodes. Remember, in this, so 1 has only one connection. So here, there's only the number 1. 2 has only one connection. Here, there's only the number 1. 3 has 2 connections. So here's the number 2. So this seems to be working. Yeah. And the spectrum of this Laplacian will be 0, 1, 3. And 3 is a simple eigenvalue. So you see, this corresponding eigenvector is this guy here. And then if you try to solve this equation, 1 to power L plus 1 to power L to power L, this will be always non-zero for all L. So this is versatile for any row. This graph here, although it's super trivial, right? So it's just 2 guys connected. So let's see what happens. So this is the Laplacian of this graph. In the diagonal is 1, 1. Off diagonal is minus 1. The spectrum of this guy is 0, 2. 2 is a simple eigenvalue. The corresponding eigenvector is minus 1, 1. And this is 0 for every L odd. So this graph is never versatile. So this means the theorem I'm going to prove never works for only 2 coupled systems. Then I spoke to a guy in Oxford. So he does combinatorics of graphs. I gave a talk like this. He said, oh, let's solve the problem for every graph. Apparently, he's never found a solution. But what we cannot prove, but I have a conjecture, is like, what you have now is a group action in the graph. So if you send 1 to 2, 2 to 1, you send the graph invariant. So this is a symmetry of the graph. Conjecture. Whenever you have a group action that's sending the graph cannot be versatile. So this means I do not know whether this is correct or not. So I think this is correct. And this means whenever you have a group action, you cannot solve the Turing-Smale problem. Not really. No. No, I mean, you have a subgroup, right? So because you can, I mean, I don't know. Now it's complicated. So if you say, if I restrict to polydiagonals, then, so let's say if 1 and 2 is synchronized, then I can have this group action, right? But this means, yeah, but I have to put this word synchronized. Yeah. Okay. So now I have all ingredients, right? So I have the versatility. The graph must be versatile. Random graphs usually versatile. If the graph is very heterogeneous, it will be versatile. So homogeneity is the main problem in this case. And yeah, so you have this versatility condition. So the corollary now will be the following. When the isolated system has dimension at least 4, so we're talking the cells will be described a differential equation. This differential equation has to have at least 4 equations. And you have skewness condition with at least 3 orthogonal vectors. So this is the question that you had. And the graph is at least 2 versatile. Then the network will have a reduction to a 3-dimensional manifold. In this manifold, you can parameterize the manifold. And if you play with parameters, you can create a Shunikov loop. And because you have parameters, you can break the loop, and you can have chaos. So what I want to do is just to tell you what's the Shunikov loop and how to break it. Yeah, just this will be the program now. But this will be the main theorem. I obtained this main theorem as a consequence of the other reduction. Yeah. So when I want to create this new vector field in the manifold, break the loop, and do this business, you need all the nonlinear terms. Yeah. Okay. So step number 1, so step number 2 is what we call dynamics on the center manifold. So this only means like at the end of the day, at the end, you finish with a vector field with a system in 3 dimensions. This is actually, philosophically, is very interesting, right? Because network problems, they are very high dimensional. If you do the simulation, you see high dimensional dynamics. But what we're saying is that the true dynamics is three-dimensional. Okay, so after you do the, by the way, I'm going to have a Jordan block. So just say, let's write the Jordan block here. So the Jordan block will have 0, 1. So this will be the Jordan block in dimension 3. And what I'm going to do, I'm going to put parameters here. So let's say I put parameters in this guy. So let's say mu. And then I change parameters. All the coefficients will change, right? And this will change. So if I change parameters, all coefficients will change because all coefficients will be functions of this guy. But you can prove that from this Jordan block, you can get any matrix you want if you put 3 parameters. So I'm just saying, if you put 3 parameters in the Jordan block, you can get any matrix. So this is slightly magical, no? So with only 3 parameters, if you have the Jordan block, you can get anything. This was proven by Arnold in the 80s. So the idea is the following now. So if I can put anything, so let me draw the 3-dimensional system like this. So I can play with the parameters such that here, now. So what I say is the following. So these guys, they will march and they will all hit 0, no? After the perturbation. And when I break the 0, I can break these guys to be complex and one to be unstable. This is basically what I claim. And now, there will be a direction where this will be the complex pair, and there will be a direction where I go off of this manifold. So let me draw like this. And now, because the nonlinear terms did not vanish, I can prove the following thing, that this unstable direction will come and will hit this plane. When it hits the plane, then I have this, I have something that Iberê studied this a lot. This is called homoclinic. This is called a homoclinic orbit. Because if you take a point in this set, if you march it forward, it's going to 0. If you march it backwards, it's going to 0. So now I can prove that I still have parameters. When I break this loop, so this guy will break, it can break in 2 ways, right? So it can either break and going down. In this case, I say I did a bad job. Or it can break going up. If it breaks going up, then I can prove that near this breakage, near the break, there is infinitely many orbits. There will be infinitely many orbits that never leave this surrounding point. Many of them will be periodic, will be countable, and there will be an uncountable number that will never close. So this is, we call this chaos. If you want to be more formal, what you can prove is that there will be a small box here, that you can conjugate the dynamics on this small box to a shift in K symbols. And the shift is fully chaotic and so on and so forth. But so that would be the main idea. So the main idea is like, let's go back. So it's kind of historically interesting because when Smale proposed this problem, the theory that you have to use to prove this did not exist in the 70s. This was developed by Hirschbill and Shu in the 80s. So this means Smale was super clever, but he could not solve this problem just because the mathematics was not there. And philosophically, what's the idea? You start with a problem. The problem is very complicated. The dimension is huge. And you massage the problem, brute force, to bring it to low dimension. Once you bring it to low dimension, you use low dimension techniques. Although the theorem is, the system is very high dimensional. I will stop here. I will not bother with the more details, but if you have questions, I'll be super happy to address them. Thank you.
So we have time for questions.
The results are very nice. Congratulations. Have you explored an example, a real example in details, to see the structures, how they form?
Yeah. Numerical simulations, you say. Yeah.
That's nice.
Yeah. But yeah, this was the... No, we did some numerics. There's lots of things I'm not saying. For example, I did not say that this manifold is attractive. This construction could be unstable. And then you have to cook up the example, the manifold's attractive. We had did this. But Fernando itself, he did not want to do many simulations. And I also didn't want to do lots of simulations. So this, we had the examples in Python, but we never actually published.
Which kind of system do you consider for simulation? Which kind of systems do you consider in the simulations, in the numerical simulation? The Schur circuit? Or?
No. Yeah. So the Schur circuit we would not consider because Schur circuit is three-dimensional. So you can think of a modified version of Schur circuit, where you have the circuit and a direction that you contract a lot. So this is the example. It's like paper-made, handmade.
Any more questions?
Can you go back to the first equation you had with the model? Yeah, that's that. So the condition on F is the skewness condition, and the condition on W is the versatile condition. And what did you say about D? Maybe I missed that.
Oh no, D. We proved the following, that for every F, there is a D, such that the system will have the effect I want. And what we prove is that if you consider, because basically it's the following, so in this business, this is important actually, so also for us doing research. So if you're analyzing a very complicated problem, the problem is super complicated, what you should look for? You should look for the number of eigenvalues hitting 0. And this is a classical, this gives you all the bifurcations and so on. So we knew this, of course, and then what we do is the following. So after you block diagonalize, let's prove that for every A, there is D. The D is not unique. The D will come in families, but we didn't care. Such that A minus D will have a block sitting at 0. Why is it important to have a block? Because when I put parameters and change parameters, then there will be this theorem by Arnold saying that from this block you can get anything. So, but D is given. So, given A, given F, there is D. Yeah.
More questions?
Excuse me. Yeah, nice conference, but talk. Could you give us an example, a real example? I mean, a real meaning, which is the form of F that will, in dimensions greater than 3, I mean, you say it starts 4, and in which you obtain the chaos in the network.
I can give you the example, but I cannot write on the board right now. I do not know off by heart. But
It's not what?
I do not know the example off by heart.
Oh, I'm sorry. Okay.
Yeah,
Okay.
but it's rather ugly, but we have it. It's just us, yeah. But I can send you over email.
Sorry?
I can send you the code. Yeah. Yeah. Yeah.
So this would not work for the fully connected network?
No.
No. Although there are dimensional reduction for...
This is a super interesting question, actually. I mean, you already got the points. I'm super upset this does not work for fully connected networks. But I think in this case, it should be more interesting. Because what will happen is the following. So how do we get this construction? The construction to prove versatility, is to be able to construct the loop. If you do not have versatility, you will not be able to construct the loop. But nothing says that you cannot construct other objects that are more complicated. So usually they will have to have symmetry, right? So let's say, once I do reduction, all the quadratic coefficients die, only the cubic. This most likely means that you can send, the group action inversion of the axis. And this means, like, if you have a clever student, he can work out, and maybe you have a Lorentz normal form. So this means, like, dynamics gets more interested. So whenever you have a restriction that this construction does not work, it should be more interesting. So fully connected graphs, the normal form of this problem should not be the homoclinic loop, which is called the Shunikov loop, but maybe it's the Lorentz. But man, this is super quickly gets complicated. I got bored of this problem.
Any more question? I don't think it.
First of all, thank you for the very nice talk, Tiago. Have you extended your treatment to discrete time systems like coupled maps, for example?
No, but this should not be a problem. But I never tried. The true honest is I didn't try.
Yeah.
And I think this should not be a huge problem. I mean, from the theoretical perspective, you should go straight away, because after do this construction, if I take the time one map here, I have a family of maps. But I understand your question is like, I start from scratch with the maps, and then, yeah, I didn't try, but I think it should be possible.
Yeah. My question was essentially inspired by the fact that we actually use some dimensional reduction when we consider the synchronization manifold.
Mm-hmm.
And so this is my second question. Is the synchronization manifold kind of normal form reduction as you did, or?
Yeah, no, but I mean, it's a form of reduction, right? I can give a super quick question, a reply, and so I didn't do synchronization manifold, but you can think of these equations if you see if xi equals to xj equals to s, and s dot equals to f of s, then the coupling vanishes, right? So this means if I start with this initial condition, I mean, equal, then I always stay. So this is diagonal. So if I here write xj and here xi, so this means if I start on top of this, I always stay on top of this. So this means the diagonal, m, is invariant.
Not necessarily stable.
Yeah. But this is a graph of a function, right? Identity is the function. But this problem, yeah, that there is multiple problems. Not necessarily stable. Maybe will not perturb to a manifold. Maybe you can break it. Maybe, but this, I think your main point is the following. So because this was n-dimensional, the dynamics of the system might be n-dimensional. This construction is slightly more complicated because this function now, the center manifold is more complicated, right? So this is the identity. The other one you have to construct. Yeah.
Any question? Hilda.
Excuse me, and I'm trying to see if we could use this in some example. Imagine that you have a system which has more than 3 dimensions, and you are working with that. And when you try to find, for instance, if there is synchronization or if there isn't in this system, what you find is Riddle basins. I mean, this is very common. It happens in many times. You find Riddle basins. So if you could prove in the way that you are showing us that you could do this, that could solve this problem, if you could prove that by reduction to 3 dimensions, this system in 3 dimensions is only chaotic. So you, meaning you avoid the synchronization manifold with doing something like this. Will that be a possibility of looking at the solution of a problem with riddle basins? So,
There is a major difference between, we can change the problem, but just the Turing-Smale problems has like, for small coupling, everything sinks to 0, right? So this is trivial. For you guys that study synchronization, this is trivial. This means for small coupling, everything synchronizes anyway. No? Yeah. And riddling bases, as far as I know, like say this will be a manifold. This manifold will be unstable. And usually, if there's a symmetry action on the matrix, there will be another polydiagonal that can also be, let's say, M tilde, which can also be unstable. And these guys can, for maps, they can intersect, right? So this creates riddling. I think is more related to the existence of multiple diagonals that's invariant. And then, yeah, then you have riddling.
Thank you.
So for the we can, of course, modify the problem, but for the Turing-Smale problem, you would find it very boring because for very small coupling, everything synchronizes. Yeah.
All right.
Thank you, Tiago, for your nice talk. As you know, I'm interested in the heterogeneity of the networks. Don't you think that the heterogeneity of the networks could play a role in your problem?
Yeah. Okay, so Marcelo is asking if the network becomes heterogeneous, what happens? So there are 2 ways to make heterogeneous. One is to make one is to make F different, because you realize that F, they're all the same for every node. This, believe it or not, is the hardest case. If F is different for every node, it only helps, because you have more parameters to play. So heterogeneity in the sense that systems are more different is easier. And then there is like heterogeneity in the terms of the GCC matrix. Let's say if you have a hub, we heard this word here the other day, right? Someone that's very influential. This also helps. If you have a hub, then we can prove that the center manifold is attractive and the scales will be stable. Because maybe this is your question. This is what's bothering you, right? So we prove that there is scales, but the scales might be unstable. You don't have to have an attractor. This is what bothers you, right? Yeah. In this proof is, what did I prove? I proved that there will be orbits that will never close. They never escape the vicinity of the origin. But maybe you never see, because they did not need to be stable. But if this network had a star or star shape, right, so a hub, a scale free, then I can prove that this scales will be stable. So the network structure will play a big role.
More questions? So let's thank the speaker again.